One of the things I wanted to mention before we got into our geometry PowerPoint is that I'm very pleased with the work that I've seen so far. As I looked through the work that's been turned in, very high level for the most part. Very happy to see that. There are a couple of areas that are important for us to double check, however, and one of these has to do with the difference between an ellipse and an oval. And this is not really something that you should feel worried about if you didn't get it correct, because as you Googled and as you look online, and in fact, even in a lot of the classroom textbooks, there's confusion in terms of these terms. Often they're used interchangeably. Sometimes they're not even used correctly. And in fact, we are in very real danger of losing the distinction between what an oval and what an ellipse actually is. I think this is extremely important because as we go forward in STEM in particular, when you go into engineering, there's a huge difference between ellipse and oval. As you can tell from my background, I'm kind of a science and space fan, but planets and satellites orbit using ellipses. They don't orbit around an oval path, and you can't just take the equation for an ellipse and plug it in for an oval. It won't work. So it is important that we get our definitions in place. And in fact, if you do your job well at the elementary level, between very clearly delineating these differences between oval and ellipse, it'll go a long ways as your children go forward into later, more advanced math topics and engineering topics. So this is a case where it really is worth our while to do our job well at this level so that it pays it forward for the work the kids are going to be doing down the road. As it turns out, this is something that can be done very easily by appealing through the Van Hiele levels of 0, which is what does it look like, and level 1, which is very elementary analysis based on properties. I've prepared a little video for us to walk us through how this might be done that will not only illustrate the Van Hiele levels, but also I think help us identify some of the properties of oval, ellipse, and a circle so that we can better define these in the minds of the students.
Let's take a careful look at some of the differences between oval, circle, and ellipse. As you saw in your geometry PowerPoint, I'm sure, the ellipse and the oval are very, very easy to confuse, and this is true not only in textbooks but also for young people. But if we go back to what we know about Van Hiele, we can talk about what different features are based on what they look like. So if I put a figure like this down, it looks like a circle. And so if I put a figure like this down, we can say, well, that looks like an ellipse. And if I put a figure like this down, we can say that looks like an oval. And even if we may not have precise definitions yet, level 0 of Van Hiele will allow us to make distinctions and classifications based on appearance. And then from that appearance, we can start doing some analysis in terms of what these properties might mean. Remember, when we talk about level 1 of Van Hiele, we've gone beyond visualization and what it looks like in terms of what the properties are based on this appearance. So I'm going to do a couple of things here. The first thing I want to do is to just help you take another careful look at some of the differences between two of these figures, and that's the figure of the oval and the figure of the ellipse. And just to kind of get the ball started here, I'm going to take the ellipse and I'm going to put it on top of the oval, and you'll notice that it's not quite the same. This distance from here to here is the same. I was kind of careful when I made that, but you'll notice that it doesn't overlap perfectly, does it? There's a slight difference here. In particular, this one looks more like egg, whereas this looks more like a squashed circle. And that's the language, in fact, that a lot of the textbooks will use. They'll describe an ellipse as a squashed circle, and they will describe an oval as being egg-shaped. So we're going to take a few minutes here and just analyze a little more carefully what these shapes look like in terms of their properties in keeping with level 1 of Van Hiele. And we're also going to take opportunity here to really make sure we understand the differences so that when it's time to teach the vocabulary going along with oval and ellipse, we can do so powerfully. To get started, though, let me go back to our friend the circle. And if I put the circle here on the Cartesian grid, one of the features of a circle is that the center point, or the center of the circle, is the same distance from each of the sides. That's the radius, isn't it? And so if we take this as the center point, we could draw a number of possible radii. This could be a radius from here to here. This can be a radius from here to here. This could be a radius from here to here, and so on. As we think about these radii, you might ask yourself, well, how did I know where the center of the circle is? Well, I made use of one of the techniques we describe in the textbook, and that's paper folding. I can fold this along a diagonal, and you notice what I've done is I've created a line of symmetry. And as we can see here, I could fold it again, couldn't I? And it completely overlaps. And because of this, we've now created yet another line of symmetry. And because this is a circle, and all the radii are of the same length, I could continue folding it and continue folding it and continue folding it. And every time I do this, I'm creating another line of symmetry. So when we think about a circle, one of the features of a circle is that it has an infinite number of lines of symmetry. And so this is a very, very symmetric object. It has multiple lines of symmetry, each of which can be demonstrated using paper folding. So let's go ahead and make a little note over here about the circle. One of the things we know is that if we were to label one of these radii, let's just call it A, so we'll have A there. Every radius will equal A. And there's an infinite number of lines of symmetry. So I have infinite lines of symmetry. Now, this turns out to have an interesting correlation here. We only have one measurement, and that gives rise to infinite lines of symmetry. Let's see what happens when we have something with more potential measurements. In particular, let's go ahead and we'll go from the circle to an ellipse. And let's see what happens with an ellipse. Well, if we think about an ellipse and we try to say, okay, how many different ways can I fold this so that it folds over and perfectly matches? I can do it once. See, there's one. So there's one line of symmetry. I can fold it again. That gives me two lines of symmetry. If I try to fold it again, though, it doesn't work. In fact, you can see that. It doesn't fit properly. And there's not another way that I can fold this to give me another line of symmetry. So when we think about an ellipse, one of the properties that we have of the ellipse, if I line this up just right here, it'll be a little easier to see, is that it has two potential lines of symmetry. It has this line of symmetry, which we could fold on. In fact, we did. That's how we generated it. And then we have this line of symmetry. And because it's a line of symmetry, we know then that this distance, we'll call that A for now, and this distance will be the same. And the reason we know that is it folds over just perfectly. We also know then that the distance from here to here, we'll call that B, and the distance from here to here, we'll call that B, is also the same. So B is equal to B, A is equal to A, and we have two lines of symmetry. So when we think about an ellipse, a couple of its properties. First, we have two possible measurements that we could make. And we could measure A and we could measure B. Each of those gives rise to a line of symmetry. So we have two lines of symmetry. You notice that here we had one measurement giving rise to an infinite number of lines of symmetry. Here we have two measurements possible that gives rise to two lines of symmetry. So as we take a look, we can start seeing some difference in properties, can't we? As we take a look at the circle and as we take a look at the ellipse, we notice that just in terms of these potential measurements and in terms of the lines of symmetry they generate, the circle is definitely more symmetric in terms of having multiple lines of symmetry. So let's take a look now at the oval, or the egg-shaped, and I'm going to make a note of that as we think about an oval, and we want an easy way to remember that. If we think back to the root word for oval would be ovus, or egg. So literally what this is telling us is that the oval shape really is an egg shape, and if we try to create lines of symmetry here, using paper folding, I can fold it exactly once and have everything match up. If I try to fold it again, as you can tell, it doesn't match up, does it? It only matches up in one direction. So when I think about what kind of measurements that gives me, if I put it on our Cartesian grid here, we have a distance along the line of symmetry from here to here that we could call A. And we know, because here's my paper fold, this distance from here to here is also A. Now when we look at our other two distances, we have this distance from here to here, which is B, and we have this distance from here to here, which we can call C. And you'll notice that even though A is equal to A, as we can show by paper folding, B is not equal to C. And that's a characteristic of the oval, that this distance is not the same. This distance from here to here is not the same as this distance from here to here. And so in this case, we know that our distance C is quite a bit bigger than our distance B. We can see that from visual inspection. So just in terms of going from what does it look like in Van Hiele terms to analysis in terms of what are some of the properties that we can find out due to paper folding, we can see very easily that there are differences that are non-significant between these figures. The circle is pretty easy to see, but these are the two that the textbooks tend to have a hard time with. And as you looked on your Googles and you looked on the internet, I'm sure that you saw that even online there's a lot of confusion between what is an oval and what is an ellipse. And you might even have found the same picture in the same place. Well, that's not the case. We have to make sure we realize that. That in an ellipse, you have two lines of symmetry. And in an oval, you only have one line of symmetry. I find it rather interesting that the fewer potential measurements, see there's only one measurement there, you have infinite lines of symmetry. We have two potential measurements here, gives us two lines of symmetry. Here we have three different measures, A, B, and C, and that only gives us one line of symmetry. We could probably push that a little forward, saying that if there were more measurements possible, it's doubtful that the figure could even be symmetric at all. This gives us kind of a sense, I think, not only of how we can utilize these levels of 0, visualization, and 1, analyses from the Van Hiele framework, and can use that to generate more careful distinctions to go along with our vocabulary. So now as we're generating vocabulary only using level 0 and level 1 from Van Hiele, we're getting very, very precise in terms of what these definitions might mean. This is crucial because we are in danger of actually losing the distinction between oval and ellipse.
So in summary, I hope this helped you better identify these properties. Again, you don't have to use anything other than Van Hiele levels 0 and 1, which is good for us in the elementary because those are the levels of our students. And we can do a good job making sure that these are clearly in the students' minds, as well as being able to draw them and represent them in a meaningful fashion. Hopefully, this demonstration helps us make better sense of the properties of oval, ellipse, and circle. You'll notice again, we didn't make use of anything other than Van Hiele level 0 and 1. And we were able to draw some conclusions based on paper folding, based on observation, based on simple analysis. One of the more interesting was that the more measurements that are possible, that are different, the fewer lines of symmetry. Remember the case for the oval where we had 3 different measurements, A, B, and C, and that these 3 measurements caused us to only have a single line of possible symmetry. For the case of the ellipse, where there was only 2 measurements possible, A and B, remember, then that tells us that there were 2 lines of symmetry. And for the case of the circle, where there's just the measurement A for the radius, there's an infinite number of lines of symmetry. The other thing that it helps us do, I think, is it helps us get a better way of how to draw these figures because we can use these lines of symmetry as a way of laying out a template, if you will, so that we can better sketch them when we go to represent them in our classroom. Please do your part to keep these terms separate and distinct. We are in real danger of having these 2 terms merge in student understanding, and it would not be to their benefit. We really want to do a good job of making sure that oval and ellipse are firmly understood.